All right, today we're going to finish up the Flash. And we talked about the 3D NAND Flash architecture last lecture, and here is a quick recap. So basically, we have multi-tier of those structures. So basically, this is a vertical string, and the string has this core shell structure. And in the core, there is an oxide, and then surrounding the oxide, we have the polysilicon channel. So that is the channel of the transistor. And then we have the ONO structure, the charge trapping gate stack surrounding the channel. And then after that, we have the metal gate. So here, this is like the schematic for the 3D architecture. And pay attention to the staircase contact. So we need to make those staircases to get connected to the word line at each tier. And this is just a quick review of the gate mask fabrication process used for the charge trap. So this is the mainstream technology used by the industry today, including Samsung, SK Hynix, Kioxia, Western Digital, and Micron. So let's repeat one more time. So basically, you deposit multiple tiers, like the nitride and oxide sandwiches, multi-tier, depending on the number of layers you want to fabricate for the 3D NAND flash. And then you etch the hole. This is like the screen or the pillar. You use one lithography to define this whole pattern, and then you etch through. And after that, then you sequentially deposit the ONO structure on the side wall, and then the polysilicon on the side wall as well. So you have formed this kind of structure here. And then you refill the core with the oxide, so you have the yellow part in the middle. And after that, we etch the slits. So basically, you cut the word lines. And after that, we remove the pink region, which is the nitride, because here we have to refill with the metal to fabricate the word line. So here the blue part is the metal, and after that we etch through the metal. So this is the key steps for the fabrication. And the other approach used by Intel is the gate first process. And Intel still uses the floating gate transistor for the 3D NAND flash. So in this case, still we have multi-tier of this kind of oxide and nitride, and you etch through. And after that, we are going to deposit the gates, like the interpoly dielectric first, and then the floating gate. So here, this like a light blue color is the floating gate, and then you etch through that, and then finally you form the channel. So here is the gate first and the channel last fabrication process. So here we will not spend too much time on the fabrication. This is not the emphasis in this course. Okay, so let's move on. So let's look at the real product. And after a few years R&D, if you recall, the first paper on 3D NAND flash appeared in 2007 at the Symposium VLSI by Toshiba. And then after a few years, Samsung first announced the commercialization of the first generation 3D VLAN in ISCC 2014. And let's have a quick review of this paper. So this is the first generation that you can buy from the market. So this chip, this is the die photo of the chip, and in total it has 128 gigabit, and it has two planes. And here you see the page buffer, basically like a sense amplifier and so on, and we have all the peripheral circuits, and also here in the middle you have the row decoder. So in this particular case, the first generation has 24 word lines, so this is 24 layers, 3D NAND flash. And then here there are some other specs. with the I/O interface. It uses similar like DDR interface to prefetch multiple bits, and then you burst out at the I/O, so you can improve the read bandwidth. So let's look at some of the reverse engineering images under the microscope. So this was done by the ChipWorks, and later I think this company was acquired by Tech Insight. So basically this is a company to do the reverse engineering. So they got the chips from different vendors, and then they peel off the package and then cut the chips into cross sections, and then they take the images and try to reverse engineer what's inside in the chip. So here is a cross-sectional view of the 3D NAND flash by Samsung, and you see that this is a bigger view. So here this is the memory array region, and here you do see the staircase, and you have many word line contact here. And if you zoom in this part, you will see the vertical string. So here this is isolation. This is night region is isolation. So here the real string is here in the dash red box. So here this is a real string. Here is a real string. And if you look at the top view from the top, if you really zoom in, you see those like a whole area, and then you etch through that hole, and then we fabricate this kind of core shell structure as we discussed before, right? So here in the core, you have silicon dioxide as a core, and then you have the polysilicon channel, and we have this let's see, this. So I think this should be in the ONO. I don't know why there's still some silicon nitride. That actually should be ONO, like charge trap stack. And then the electrons will be stored in this middle silicon nitride. And then we have the tungsten as a metal gate. And I don't know why there is still some silicon nitride. So this is the basic structure for the 3D NAND flash, first generation from Samsung. You see here, this is a very good profile in terms of the vertical etching. So you make the like a very high aspect ratio, like trench, or you can call it hole, to etch through that. So the challenge for the fabrication will be how you etch through this multi-tier, like oxide and nitride sandwiched structure. So here are more details for the first generation of this chip. So again, this is a schematic for the 3D net list, the circuit symbols. So you have those vertical strings. Each string is a land string, and then you have the top string select controlled by the SSL, and SSL, as we discussed before, are separated. And then you have the word line. So here you will have the word line 0 to 23, because here you have 24 layers. And then at the bottom you have the ground string select. And then at the very end, you have the common source line. So here one block has 8 strings, 8 SSL. So from SSL0 to 7, so this is like one block. So if you look at the block size, so here, let's say the XYZ for one block. In this particular case, On the x-axis, so in this direction, it says there are 8 SSL. And on the y direction, here's how many bit lengths? How many bit lengths? It says there are 8 kilobytes. 8 kilobytes. That means 16K bits. That's 16K bit lengths along the y direction. And then z direction, of course, here it says 24 word lengths. So we have 24 word lengths. So you see one block, it has 8 SSL, 24 WL, and 16 kilo bit lengths. So this is one block for this particular chip. Of course, you have many blocks on the chip, and in total you have 128 gigabits. Question? Oh, 64, yes, all right. All right, so this is and then here this is the cell characteristics of the 3D VLAN. So compared with the two-dimensional LAN, there are some advantages of this 3D LAN. And you can understand this through the geometry of the structure. So here, first of all, the VTH distribution is more tightened in the 3D NAND flash compared with the 2D NAND flash. So here we show the 3D NAND flash in the blue curve, and then the 2D NAND flash in the 1X generation in the red curve here. So here is more tightened distributed in terms of VTH state. And also the coupling, the cell-to-cell coupling, as we discussed before, is a big concern for the 2D flash because the reduced dimensions between the word lengths or the bit lengths. When you program the adjacent cells, then the VTH may shift after the adjacent programming or coupling. But for the 3D NAND, this shift is very minimal. So here you can understand the reasons behind those observations. So here the VTH distribution is more tightened and the cell-to-cell coupling is reduced. So the reason is that the 3D NAND flash, actually if you look at the area for the floating gate or charge trapping layer, actually is much larger than the 2D NAND flash. Why is that? Because in the 3D NAND flash, let me ask you the question, what is the area for the one single charge trap transistor or one single floating gate transistor? What is the gate area? What is the area? So you need to consider the geometry here, right? So it's a core-shell structure. And then this is like a top view. So if you think the diameter, let's say radius is R, right? And then the perimeter of this one will be 2 pi R. And then if you look at the side view, then you have the, let's say 2 pi R as the perimeter of this one, and multiply by the edge, the height of each layer. So basically this, so the side wall of this cylinder will be your gate area, right? So this is the channel area or the gate area. Channel or the gate area will be this 2 pi RH. And in the two-dimensional NAND flash, we discussed before, it's just F square, right? One cell, you know, is 4F square, but actually the gate area is F by F in the 2D case, in the two-dimensional space. So those parameters, for example, the radius is much larger. As we discussed before, we relax the lateral dimensions in the 3D NAND flash. And the radius can be like 60 nanometer or even 80 nanometer. And edge can be like 30 nanometer. So you can calculate that. And F, for the 2D flash, we already scale to 1x. If you think 1x is like 18 nanometer, you can calculate the area. So this one, 2 pi RH, will be much, much larger than this F squared in the 2D case. In other words, the surface area for the 3D NAND flash is much larger. Therefore, you can store much more electrons in one cell. So you can relax or relieve the problems of the few electrons as we discussed before. And you have done that in your homework, right? So only certain number of electrons are stored in the floating gate or the charge trapping layer, depending on the geometry. So here we will relax the geometry dimensions. Therefore, we can store much more number of electrons in the 3D NAND flash compared with the 2D NAND flash at the scaled node. And also, the distance between the cells is relaxed. For example, the 3D screen, right? So here, typically, like from the layer to layer, we have 30 nanometer to like 40 nanometer distance. So the coupling is also reduced. Therefore, here the cell-to-cell interference is reduced. And in the 2D case, so as we discussed, this is only like 18 nanometer or even 15 nanometer today. So the cell-to-cell coupling, the capacitance in the 3D case is relaxed. So the whole idea is that we use the third dimension to relax the physical distance, because now you can build higher and higher strings. Therefore, you don't need to make the two cells too close to each other. Therefore, this cell-to-cell coupling can be reduced. So any questions here? And at the chip level, so here is a comparison between the 1x nanometer two-dimensional MLC versus this first generation 24 layers 3D VLAN. So here you see the memory capacity doubles from 64 gigabits to 128 gigabits. And also the other metrics, like the write bandwidth increases, and the chip density. Here what we care about is this one. Gigabit per millimeter square. So how many gigabits you can pack on 1 millimeter square area. So here you can get close to 1 gigabit per millimeter square for this first generation 3D NAND flash. And also, if you use this 3D NAND flash in the system to build the SSD, and then you run the workloads or your applications on the system, and here is a comparison between the 2D NAND flash versus the 3D NAND flash. And in terms of those workloads, like sequential write, random write, and the average power, peak power, you do see the benefits at the system level. If you measure the power and the throughput at the system level on the board, you also see the improvements. So this clearly suggests 3D NAND flash could be the way to go at 2014, around that time frame. So this is a summary of the first generation 3D VLAN, and I will not repeat that. So here, yeah, you can review those specs. So after that, I believe Samsung publish every year in ISCC, the major circuit conferences, about their new generation of the 3D VLAN. Until today, it has been like 7th or even 8th generations. So let's look at the second generation, which is ISCC 2015. And in this case, so it improved to 32 layers. And also it enabled the TLC, the 3-bit per cell, triple level cell. So the density in terms of the gigabit per millimeter square, if you recall the first generation, close to 1 gigabit per millimeter square. And for the second generation, it improved to about, let me see. So this is like 1.6 or 1.7, almost double the integration density. And it actually outpaced the hard disk drive density at that time. So this one, so I will not go into the details of the organization in terms of the number of pages and the number of blocks and so on. So you can refer to that. But here you look at the like erase time, programming time, and read time. So those are typical numbers. Block erase, like you need 3.5 milliseconds. Program, 700 microseconds, especially if you want to do the TLC. As we discussed before, you have to spend more time for the ISPP, the write and verify. And the random read, you need to spend like 45 microseconds. And then this is the third generation in 2016. And the density further improved to 2.6 gigabit per millimeter square. So in this case, the number of layers become 48. And then the other specs remain similarly as before. So you see the trend is generally make more and more vertical layers. So from 24 to 32, 32 to 48. And I believe from 2014 to 2016, Samsung was the only company that can offer the commercial product for the 3D VLAN. And starting from 2016, all other competitors catch up, and they start offering the 3D VLAN product as well. And 2017, this is the fourth generation from Samsung. So I will not go into the details. The only feature I want to highlight, this becomes 64 layers, and then the density get close to 4 gigabit per millimeter square. So this is a landscape of the 3D NAND flash competition back in 2019, like 2 years ago. All major companies start building the 3D NAND flash. It's like you build the skyscrapers, like very tall buildings. So you look at the height of the 3D NAND stack. So it's like a micrometer, a few micrometer height. If you look at the vertical string height. So here all the companies start building like around 96 layers back in 2019. So here I just want to highlight one challenge in the 3D NAND flash. If you start building more and more layers, what might be the limitation on how many layers you can stack? So from the fabrication perspective, the edge is a problem. So the aspect ratio is very high, right? So we need to dig a very deep trench, something like this. So the aspect ratio is very high. You may have like a 100 nanometer here, and we see earlier you have like a few like micron, 6 or 7 micron meter there. So the aspect ratio can be like 80 to 100. It's very difficult to etch through this like deep trench. And then the thing is that you need to think about the angle here. If you think about this angle, if you cannot make it vertical, if you have a certain angle, so let's say maybe here this angle, this theta. So this angle, if you can make it perfectly vertical, then of course with the increase of the tiers, then the cell size equivalently will reduce. But if you cannot make it vertical, then you have this kind of angle. Then if you stack more tiers, actually on the top, you have to pay for more additional lateral space. Then not necessarily the more tiers you stack, the smaller each cell equivalently is. So if you cannot make this very vertical, then you will not win here, as we show here. If you have only 89-degree sidewall in terms of the etching here. So very difficult to make very vertical. Therefore, in the real manufacturing, nowadays the industry mainstream is to have multi-deck fabrication. So if you can only etch 48 layers, if that's the limitation, then you have to split your fabrication into 2 tiers. This is undesired, as we discussed before. You want to use one lithography to etch through. But due to the limitations by the etching, so you have to split the fabrication into 2 deck. So this is first deck, this is second deck. So you will etch, if you look at zoom in, you will etch this first and then do the second deck second. Because at one time, it's very hard to etch through this like very high aspect ratio. If at one time you can only etch 48 layers, you have to split total 96 layers into two deck. So this was introduced by Toshiba and Western Digital when they fabricate their 96 layer BICS, this bit cost effective structure. So this 2 deck fabrication is introduced to overcome the challenges of the etching. You have to split the litho into 2 steps. Of course, you will add on a little bit of fabrication cost, but this is unavoidable. And here I just summarize the recent industry trend in terms of the competition of the number of word lengths, number of layers, and many companies introduce the 2 deck fabrication, even at 64 or 96 layers. But Samsung didn't use the 2 deck fabrication. Still, I believe their latest 176, they didn't disclose clearly, but I believe they use 2 deck in the 176 here. So today, this is the typically around 176. This is 2021 today. Most companies can offer 176 layers 3D NAND flash. And it was projected next year or two, it will reach to 256 VRAMs. So here this trend is going to continue with more and more innovations. So any questions so far? Okay, so next we will introduce some new concepts in the 3D NAND flash. And one of that is the CMOS under array, CUA, or the peripheral under CMOS, PUC, or CMOS under array. So the basic idea is that we hide some of the peripheral circuits underneath the 3D NAND flash core area. So previously we may have the core area, and then the staircase, and then the peripheral circuits like your sense amp and so on the horizontal dimensions. Now we want to hide some of the peripheral circuits underneath the 3D screen area. So this is called CMOS under array. So this is the CMOS, and this is your array with the vertical screens. So here this is a schematic to show the concept. The peripheral transistor is fabricated first on the silicon substrate, and then we do the 3D screen afterwards. So this is more like a monolithic 3D integration. And another approach is called X stacking. So this is not monolithic. So in this case, you can fabricate two dies. One is a CMOS die, and another one is your 3D NAND die. And then use this copper-to-copper pad bonding, as we discussed before in the DRAM. So this hybrid bonding means copper pad to copper pad direct bonding. And then you fabricate two dies separately, and then you flip one die, and then you do the bonding. So this is another way to further improve the array efficiency. All right, so last two slides to summarize the latest chip performance. So this is the latest from this year's ISCC. And this is the triple level cell, TLC, 3-bit per cell, from major companies. All of them are around like 170 something, probably 176 layers. And here up to 1 terabit per chip. And the die size is here up to like close to 100 millimeter square. And the density reach 10 gigabit per millimeter square. If you recall, the first generation is close to 1 gigabit per millimeter square. And after a few years, you see this density increases by 10 times. And then there are other parameters like the programming time, latency, typically hundreds of microseconds for the TLC programming, and read latency is typically 40-50 microseconds. And all of them use the CMOS under array technique as we just discussed. And one more slide on the QLC. So this is 4-bit per cell. and all the major companies offer that option as well. But here, this data was from 1 or 2 years ago, so the number of layers is like 96 for the 4-bit per cell. But since we have one more bit in the cell, so the capacity can still achieve like 1 terabit, even though you have less number of layers. But each cell can store one more bit, so still you can reach like terabit per chip. And the density-wise, Intel one this year, they have 144 layers, reported the highest density, up to like 13.8 gigabit per millimeter square. Thanks to this 144 and also 4-bit per cell. But here, one trade-off as you compare with the TLC. So the program latency will be even slower. So it will be like a millisecond. Because as we discussed before, 4-bit per cell, you need more verify cycle for the ISPP. And also read latency will be slower. So basically you can have more density, or let's say lower cost per bit, but you have to pay for the performance in this case. A question? It's not DEX. Planes is different. Planes, if you look at the die photo here, so planes means how many independent like a plane you can operate. Deck is the vertical concept. If you look at cross-sectional view in the fabrication, then DEX means how many fabrication steps you have to go through. So that different concepts. Okay, a quick summary. So NAND flash, as we discussed, dominates the market today, and the 2D NAND flash already stopped at 14 nanometer node back in 2015. And to further increase the density, so we have to rely on the MLC, TLC, QLC, and even people are talking about PLC. This is 5-bit per cell. Peta, I believe peta level cell, something like that. But with the MLC, TLC, and QLC, then the reliability will further degrade because the margin between the levels in terms of the VTH will further reduce. And we will see NAND flash continue the effective scaling with more and more layers, and also with the techniques like CMOS under array to further boost the array efficiency. So NAND flash will still dominate the market, I believe, in the next 10 years or so. There's no technology that can compete with NAND flash in terms of the cost per bit, because it's so cheap these days for the 3D NAND flash. All right, any questions? If no, then we'll stop here for the lecture.